This is the lesson video for A3, Area of Circles and Regular Polygon. Please be sure to take notes, make them good notes, so pause the video to think, catch up with notes, add ideas to the side, something I said but didn't write that was helpful to you, or questions you come up with to ask your teachers. And be sure to complete those A3 introduction problems. So as we have been working with triangles and trapezoids and kites and things like that, our goal in this section is to look at regular polygons and to look at circles, and to not be worried about memorized formulas that we've heard in the past, is to think where these formulas came from so we can connect. With the two regular polygons that you see, we need a method to be able to get the area that would work for any regular polygon. I could take any polygon I wanted, regular or not, and break it with a ruler into shapes that I do have area formulas for. Maybe I'd break it into a trapezoid plus a triangle in this one. Maybe I'd break this into 3 different triangles and calculate their areas. But our goal in this section is to not have to think through every regular polygon problem individually, to be able to put them together in a way that would work for any regular polygon that were given to you. So if you were in class, we would try this and have groups try to come up with a way to do this. Instead, we're just going to suggest ways that have been found. I could break that pentagon that's regular into 5 triangles going to each of the vertices from a center point. Because the polygon's regular, I would know that all of those sides were identical. And if I was truly at the center, I would know that what is referred to as the radius of that, though it's not a circle, that all 5 of those lengths would be the same. And therefore, I'd be able to split my regular pentagon into 5 isosceles congruent triangles. And if I could get the area for one of those triangles, then I could get the area for all 5. I could do 5 triangles that were identical. Going to the dodecagon, I could do the same thing. I could break my dodecagon into 12 congruent triangles, and therefore get the area of 12 multiplied by the area of 1 triangle. So our goal for regular polygons is to find a way to do that. In order to do that, I'd have to be able to get the area for one of those isosceles triangles. So as I look at that isosceles triangle, I do know that the side length would become the base of my triangle. So if I knew the side length, I'd have the bottom or base for my triangle area formula. But the height is what I would need, and the height is not one of those radius lengths. That height or altitude that I would need is a different length than that radius length in a polygon, so I would need that information so I could use our plan. So some vocabulary. An apothum, sometimes pronounced apothum, is that perpendicular segment that we see. So by definition, it's a perpendicular segment, and its endpoints are the center of a regular polygon and one of its sides. And they only exist on regular polygons. And by measuring that length, that would serve, so the apothum or apothum would serve as the height for each of our triangles. Then if I draw in those radius measures out to my vertices, those are going to be the other 2 sides of my triangle. My side length here is going to serve as my base for my triangle area formula. So if I had a plan to get the area for any regular polygon, I'd be using the area of a bunch of identical congruent triangles, and I'd have to know how many I had, times the area. So when I go to put all this together, there's 2 formulas to calculate area of a triangle, and we'll put them into your conjecture in a minute, so don't worry about getting these written down at the exact moment. But what we'd be saying is that for our triangle, our side length times apothum times half would calculate the area of the triangle. And n would be the number of triangles that we had. Another formula that shortcuts that, and we will need both for calculation flexibility is that number of sides times side length for any polygon that's regular is perimeter. So this formula can be rewritten as 1/2 perimeter times that apothum. So let's do one and then we'll formalize the formulas so that you can write them down. What's the area of the blue triangle? They have a nice 9-sided polygon here. Oh no, it's 7. So there's 7 congruent triangles in this shape, so that's my number of sides. The area of the blue triangle would be a 1/2, base length of 5, apothum or height of 5.2. So when I'm doing that, I'm thinking about 1/2. The side length is serving as my base. The apothum is serving as my height. That would give me an area of 13. There are 7 of them, so I'm going to multiply my 1/2 side length times apothum times that n, 7 triangles, to get the total area here, which number-wise is 91. They did not provide a unit, so when I put a unit label, I would refer to them as square units. So formulas-wise, we said we would get you there, so you don't need to stop before. The regular polygon area conjecture includes 2 formulas so that we have that flexibility. The area of a regular polygon can be given by the formula 1/2 side length times apothum times number of sides. And I've seen that written 1/2 ASN, 1/2 ANS. The multiplier order won't matter. Or 1/2 apothum times perimeter. So we're going to go use those. Again, pause the video so that your notes have good things. We're going to try these out. I've got a regular octagon here. They told me that the apothum is 8.5 centimeters. That's that perpendicular segment. And that the side length for my regular polygon is 7. So again, I want to be thinking about that formula and how it's formed. It says 1/2 side length of 7 times apothum of 8.5 is the area of one triangle. And then if we multiply by, we happen to have an octagon, so 8. That's our number of triangles. And that will produce our area. The 7 and the 8.5 are both in centimeters, so when I multiply this together and I get 238, I'll be in square centimeters for units of area. The pentagon. In the pentagon, they gave me the apothum as 6 centimeters. They did not provide a side length, but they did provide the area. The question is asking us for perimeter, so I want to think about that formula that I do have that says the area for my regular polygon can be calculated as 1/2 apothum times perimeter. So therefore, when they gave us the area of 130.8, we can demonstrate some algebraic flexibility in showing where they got that from. Apothum can be replaced with 6 as given to us, and we'll leave capital P for perimeters are unknown. And again, we want to see some good algebra for demonstrating where your answers came from. Just a set of random multiplies and divides is not really demonstrating to us what it is that you knew about how those variables related. So as we do some algebra, we get to the 43.6 as what we think the perimeter is. Perimeter is a length, and all of our lengths would be in centimeters. And now we're up to circles. And this is a really complicated diagram when you first see it, so instead of actually looking at it, I'm going to take you to GeoGebra. Circles have a lot in common with regular polygons, but they are different. So I'm starting with a pentagon here, and we already know in a regular pentagon what apothum or apothums are. So I'm going to hide those for a moment. We've mentioned briefly that the segments from the center of a regular polygon to a vertex is called the radii or radius as well. And we said in regular polygons, those are different. Those lengths are not the same. So why bring it up? Well, in a circle, if we think about could we fit a polygon inside of it and try to make a regular polygon kind of take up all of its area instead, I'm going to first put in a 3-sided or a triangle into the center of the circle, and clearly the triangle does not have the same area as the circle. Its apothum is 3.5, the circle's radius is 7. It's not anywhere near the area we're looking for the circle. But as I put in more sides, what I'm hoping you're noticing is that apothum and that circle radius are becoming more and more, that they're getting closer to each other in length. The circle's radius isn't changing, but as I increase the number of sides of that regular polygon, filling up the space, it's getting closer and closer to filling up the space, and its apothem is getting closer and closer to being the radius. So if I could make it so that my circle were fit perfectly by one, I'd have to have infinitely many sides to that regular polygon, but what would happen is that the apothem would become the radius in length, and that's how we get it to being a circle. So to derive the formula for area of regular polygons and circles and relate them, there's several ways you can do it, but here's what we know about regular polygons. 1/2 apothem times perimeter. Well, we'd like to switch that over to what we know about circles. So area for a circle, we can leave a 1/2 in there. We said if this were a circle, the apothem becomes the radius. So the radius would go in for apothem. And perimeter for a circle is really circumference, and I'm going to do it in its radius form. 2 pi r is the perimeter for any circle. So if I simplify my algebra from that regular polygon formula applied to circles, my 1/2 times 2 becomes 1. Radius times radius is radius squared with a pi multiplier. And you've likely seen that area formula before. So the area of a circle can be given by the formula pi times radius squared equals area. There are other ways to get that. And so some students say, I'd like to see those triangles broken up so that I can see how that becomes pi times radius squared. So we will briefly just take you to one where they do that. So in this one, they actually take a circle. And first they just straighten out its circumference so that you can see if we stretched out its entire perimeter where that would land. And after we have that in place, then we could dissect that triangle into lots of different, into lots of different triangles. And we can go as many as hundreds in this one. But I'm going to put it back to a smaller number, we'll say 36. And I'm going to take each of those triangles and rearrange them. Now, the more of them there are, the closer and closer to triangles they would be because the smaller amount of a curve you would have at the bottom. So if I rearrange those, there's all those unique almost triangles becoming more like triangles the more of them I make. And then I'm going to take half of them and tip them over the top. So all the area for that triangle now, or for that circle now, is rearranged. I'm going to bring that into our document here so that we can also get that formula one last way. You would end up with a parallelogram. And this parallelogram's height would be radius, and its base would be half the circumference of the circle because half of those were tipped over to make the top sides. And half the circumference of a circle would be half of 2 pi r. And if we clean that up, that's just pi r. So as we go to work with this, we could get that the area for that parallelogram, which would give us the area of the circle, is pi times radius for base of my parallelogram, radius for height of my parallelogram, pi r squared for the area of the circle. So there's multiple ways to derive the areas for these different things. Your goal would be to have a way that you can explain and visualize as you're understanding. So just one circle practice problem. I'm going to toss this up. If the area of the circle at the right is 256 pi square meters, what's the circumference? Ooh, so we were given area, and they would like us to find circumference. Well, to calculate circumference, I know I either need a diameter or I need the radius. So out of that area, I'm going to need to get whichever of those two lengths is easier to get. And from area of a circle, it's much easier to get radius. So 256 pi would be the result of them having calculated pi times radius squared to see some good algebra. We could divide both sides by pi, and since they each have a factor of pi, we would have those no longer appearing. So 256 is our radius squared. Now, algebra-wise, we're good algebra students. We know we could take the square root of r squared to get r if we took both possible square roots of 256. This is algebra speaking. Algebra says that there are two possible values that fit that formula. Here's what algebra doesn't know. Algebra doesn't know that you're calculating something about a physical shape. So here's where algebra and geometry disagree. Algebra says that there are two solutions, and algebra is correct for that numerical equation. Geometry, however, says there's no way that that radius can be a negative number. So therefore, while we get two solutions to our algebra, and we should show them so we don't fall into bad habits, one of those is extraneous. And you talked about extraneous solutions in algebra. It works in the algebra, but it doesn't work in the situation. So therefore, when we go to calculate our circumference, we're going to come up and only use the positive value for the radius, which is 16. So circumference is 32 pi, and that's a length we'd be in meters. No approximation is requested, so no approximation or rounded decimal value should be given. So your task after you finish this is these 5 problems on your introduction assignment. Again, please watch for that extra piece that we're working on in knowing when to leave answers simplified and simplified and in terms of pi, which is all the time, unless an approximation is requested. And the way they're telling you on this sheet is that approximately equals 2 symbol would be used.